Hi. So far we tried to build our own computer with using this circuitverse simulator for logic gates, and we actually came quite far. We were building this arithmetical logical unit that could be programmed with a 16-bit input, and I think that was quite fascinating to see that you actually can control some piece of hardware with a bit pattern, and that you can define your own instructions for this device. But I also showed you that in order to actually go a bit further to build a complete computer, certain technical details have to be better understood, that we actually should maybe take some classes in the electrical engineering department. But still, we want to proceed, and in this video I will start you to show the next simulator for actually building our computer, the ULM Generator. With the ULM Generator you can specify your own instruction set architecture. It will generate from that a micro architecture, so that in the end you have a complete computer architecture. Now in this long sentence I just introduced three terms without really defining them, without specifying their meaning. Let me do this very informally, because you already have this background from the ALU project, and I want to take advantage of that. You saw that in the end the ALU could be programmed just by knowing what instructions are available. And for programming it, you didn't have to know how originally the logic gates were used for realizing this instruction set. And in the same way you can think of a computer. What is relevant for programming it is what instruction set architecture is somehow realized in this computer. And this is what you specify in the ULM Generator. Now, in the ALU project, you were also dealing with the micro architecture. You were using logic gates to build an adder, these registers for decoding instructions and executing them. And you also saw that probably with more time and better understanding, we could have achieved the same with, for example, fewer logic gates. So the hardware would then be cheaper and maybe even more efficient. But that means with a different improved microarchitecture, we could have realized the same instruction set architecture. And that's also the case in computers. You can specify an instruction set architecture, build some initial simple microarchitecture for it, some prototype, and then later improve this microarchitecture. Programs written for this computer still run on this improved version with a better microarchitecture. So this is one advantage to separate these two things. Another advantage is that in the first initial version of the computer, you just have a software implementation of the microarchitecture. And such a software implementation is provided by the ULM Generator. These are the components of the microarchitecture that are available in the ULM Generator. I will describe their functionality later in a bit more detail, so that you know what kind of features can be provided in your instruction set architecture. Now I think it's kind of helpful to have an idea how these components are also connected with each other and how they can interact with each other. The ALU and the so-called control unit are part of the CPU, and the CPU is connected with the virtual memory and the I/O devices with some data bus. In the demo I will first show you how to describe a simple instruction set architecture, how to generate from that a computer architecture, and then how to write a program for this computer, of course in machine code. And it will be not as inconvenient as it sounds, because we have a nice program loader. It not only knows how to initialize the memory with the executable, it also supports a nice format for the executables, where you can use ASCII characters to describe bit patterns. So you can use a normal text editor. You don't have to write some binary representation of the machine instructions. You can type in the hex representation in ASCII of a machine instruction. You also can use comments in the executable to make it more readable. And actually there are a few more features, but these are just, I think, in the beginning the most important. I will also show you then how in the execution that begins after the program was loaded, the control unit is responsible for this sequential execution of a program. How it is specified what the first instruction is, that is somewhere in the memory, and how the control unit determines what the next instruction will be. And actually there will be one instruction that will be the major part of this demo, which is stopping this sequential execution, and halt instruction, which halts the program with some exit code. But before I can begin with the demo, I first have to give you an idea how the format of a single instruction looks like. Every instruction consists of 32 bits, and because on the ULM we define 1 byte as 8 bits, every instruction has 4 bytes and can be represented with 8 hex digits. You can choose what part of the bit pattern of this instruction is used as opcode. And once you have specified that, you cannot change it from instruction to instruction. I usually will use the most significant bits for the opcode. And 8 bits, so that first of all, again, I can use hex digits to represent this field. And with 8 bits, I have 256 possible different instructions, which is sufficient. For the remaining fields, you have more choice. You can change the meaning of the remaining fields, how they are mapped to operands from instruction to instruction. For example, you can do it like in the ALU project to group it into X, Y, Z, and then you also have a similar way to describe the functionality of the instruction set. In the demo, I will just show you one simple instruction, which is just stopping the program, and maybe also a few others, so that we have a bit more of a interesting program that gets executed. But in general, you will see there is a clear mapping from opcode to a certain component of the microarchitecture where these other fields can be used as an operand. On the website, you find information for obtaining the ULM generator, how to get it from the Git repository. And I assume that you now have this directory ULM generator with this subdirectories here. Relevant for you is actually just this directory here for describing the instruction set architecture, and this directory here, which will contain the generated computer architecture once the build is complete. Currently, we have already 2 predefined instruction sets in these 2 subdirectories. ULM contains a more complete instruction set architecture, and this my instruction set architecture directory will be this initial instruction set architecture for this demo. Let me show you the content of that. So you see here, this is a definition for how the bits in this instruction are used for the opcode and as an operand. And we have here one definition for one instruction. Before I go here a bit more into the detail, let me show you how this computer architecture actually can be built from this description. You just have to type in make, and that's it. Hit return, and that's it. But it takes a while. At least the first time, it takes a little bit longer compared to upcoming builds when you do some modifications to the instruction set. So let's use the time command to measure how long it takes the first time. So on my MacBook, I had to wait for 1 minute, 20 seconds. And what happened here is actually that 2 computer architectures were created. And you find this in the second directory, ULM build, in the subdirectories my instruction set architecture and ULM. In both you will have the same executables or the same name for the executables like here. You will see that once you change the instruction set architecture, you have to rebuild, of course, this computer architectures. Let's just simulate that. I just write this file again, so that now it has a newer timestamp, and then I will rerun make. And now only one computer architecture was rebuilt, and also not everything needed to be rebuilt, and now it just takes 4 seconds. let's see how you can describe an instruction set architecture. In this first line here, in this example, you see how you can specify the grouping of the bits in an instruction. I'm calling this specification R, and actually you can give it an arbitrary name, for example, foo. And then I'm specifying that the 8 most significant bits, I'm always writing bit patterns from most significant to least significant, so things on the left are more significant. The 8 most significant bits I call op, for op code. And the next 8 bits, the next 8 less significant bits I call X. And you see that 16 bits are here not mentioned. But you can specify a second specification, let's say bar, where you actually mention all 32 bits. I call the next group Y. It also contains 8 bits, and the next group after that Z, also with 8 bits. So it sums up to 32. You also see that I'm using here this U. With that I can indicate that in case this bit pattern is used for an integer, it is used for an unsigned integer. And actually you also can specify that it's used as a signed integer, and there is a third option. You can use it for a so-called jump offset. But this will be the content of another video. Now, after you describe the few of such formats, you can begin with describing the actual instructions for this computer. And that's done here. Here I'm saying that if the op field has this bit pattern hex 01, I want to use a certain format from above, for example foo. And in the next line, after some indent, at least one white space, I can state what the micro architecture should do with such an instruction. And in this case, we have a instruction that should be carried out on the control unit. It should carry out there a halt instruction to stop the execution of the program with the exit code X. And that means this bit pattern here is used as unsigned integer, and it specifies the exit code. And after saving that and rebuilding actually the computer, we can write a program. Let's write a program first. It will just have one instruction with the opcode hex 01. The exit code should be 42, so in hex 2A, and the remaining bits of the instructions I can choose arbitrarily. And you see that I first of all can use spaces. The program loader will ignore them, and I also can use comments. So I can say here that this will halt the machine with exit code 42. And then we can generate the computer architecture. It should take about 5 seconds. And then we can run this program. The new build computer will be in this directory, and I will first use the command line version for it. And with that, I'm just executing this program halt. It gets loaded into the memory, then it executes this single instruction, and on the command line you can see here with echo $? That the exit code is actually 42. So this is really the result of our program. For actually seeing what happened inside of this computer, you can use a second tool that was generated, a debugger for the ULM, and it's called ULM Debugger Text User Interface. And now let's run this program with this tool. Actually, now it's not running. It was just loaded into the memory. So this is the point after loading the program before the execution begins. You see here in this window the program that was loaded. And you see that here some changes were applied. You see that this instruction was assigned to the address 0. In this window here, you see the content of the virtual memory. Currently, the virtual memory just has one page allocated and mapped to the physical memory with this address space. And most of this page is unused. You see that only the first 4 bytes contain now this instruction. You also see here the CPU with the control unit and the ALU. And this control unit has 2 instructions. And this control unit has 2 registers. This register is called the instruction pointer. It always contains the address of the instruction that should be executed next. So this is relevant for this sequential execution of a program. And now with Control R, or you also can use here this menu, you can run the program. And you can see it just started the execution, executed this first instruction, which caused the execution to stop, to halt the computer with a certain exit code. Now we can of course make this a bit more interesting by specifying more instructions. Let, for example, define a second instruction with opcode hex 02. I'm using again this format foo, which will not be relevant here because it's a no op operation. It's just doing nothing. So I'm just having here a semicolon. So you see that this line describing what the instruction is actually doing is always some valid C statement. Now let's change this program so that we take use of this instruction. Add some no op operations, and then here of course it's completely arbitrary what I use for this operand field. Then I have to rebuild this machine. It would not really make sense to run it now again on the command line because you would really not see a difference. So we again run it in the debugger. Now you see that 3 instructions were loaded into the memory. The instruction pointer is initially still pointing to the first memory cell with the first instruction. And now I will use this step to just execute 1 instruction, and then it should pause so that I can see step by step what the program is doing when I'm executing it. Now, 1 instruction was executed. It didn't have any effect except that now the instruction pointer was incremented by 4, pointing now to the next instruction. And you also might notice now that this instruction that I had here was somehow loaded into this so-called instruction register. So we have an instruction pointer for the location of the next instruction and the instruction register, which will get this instruction from the memory. And then you might guess what the control unit is doing with this. It will decode this instruction and then delegate it to the relevant component for executing it. In this case, delegate it to nowhere because it's a no op operation. Now let's execute another instruction. You see the instruction pointer was incremented again by 4, so that it's now pointing to this instruction. And now this second instruction was loaded into the instruction register. And then the program again with the third instruction just stops the execution and indicates this exit code. Now let's make this a bit more interesting by showing you how to define an instruction for the ALU, or actually a few instructions. I will first change this description to foo1, and in this description I want to call now this field xy, and it should refer to 16 bits, and the last 8 bits I want to call here set. And this I actually want to have twice, but in the second variant I want to use this field for a signed integer representation. Let's also make this a bit nice. Then I have to rename this into bar. Then I can refer with x to the same field in the instruction, so I don't have to change the program for that. This I also just rename into bar. I also could rename it to foo1 or foo2 because I'm not using any identifier. And then this instruction with opcode hex 03 should use this format foo1, and it should initialize a register with a 0 extended bit pattern specified by xy. And for that there is a micro function set register, and the first parameter gets the 16-bit input, and the second operand specifies the destination register. And actually this I can copy and just modify, because the next instruction with opcode hex 04 should use this format for initializing this register. And now you see the difference. With this here I can initialize it with a 0 extended bit pattern, and here with a sign extended bit pattern. And then I want to have another instruction for adding registers. Here I use the instruction bar and the micro architecture add 64 for adding 64 bit patterns. The first operand will be the bit pattern of the register with ID X. The second operand, the bit pattern of the register with ID Y. And the third operand is the destination register. Okay, now we generate or regenerate the computer for that, and can write a program for demonstrating these operations. So first I want to initialize some register, so opcode 03 for the 0 extended initialization with a bit pattern with 16 ones, and I want to initialize, let's say, register 1, and with this instruction I want to sign extended. I will use as an operand the same bit pattern, and then I want to add register 1 with register 2 and store it in register 3. And again here using the command line version of the computer would not be so interesting, so let's use again the debugger. And then it's interesting to watch here the ALU and to see that the first two instructions are just no op instructions, so here we will see no infect. Now I initialize register 1 with the 0 extended bit pattern, here with the sign extended bit pattern, then I'm adding these two registers, and you see with some details what kind of micro instructions are available. It's kind of easy to rebuild the ALU from Circuitverse on a higher level. So you saw the ULM Generator provides a programming language that you can use to describe in a source file your instruction set architecture, and it then generates from that the computer architecture. So for using a programming language, you have to know the usual rules. What are the available lexical elements? What are the rules for the grammar? And what functionality is available? What micro instructions in particular are available for the ULM Generator? And both will be, of course, described on the website, but I also will show you more things in additional upcoming videos.